Hi everyone. So this lecture is going to be on Thomson section 4.6, titled The Solutions to the Dirac Equation. So we've been playing around with the Dirac equation a lot and figuring out how to write them in this covariant form using these gamma matrices, right? What we're going to do now is we're going to actually find out how we can write these four component spinners that, I think I'm giving that away for now. But just to remind you guys, right, that the solutions to Schrodinger equation, there's only one, right? In the non-relativistic case, right, it's just this wave function where, psi is some normalization factor and some plane wave, right? And the idea is that if you have a particle that, is a superposition of multiple momentum, multiple energy, right, you can actually add those up and then make any arbitrary wave function out of these plane wave solutions. So the main idea is that if we are able to solve the plane wave solution, the arbitrary wave solution could be written out in just a linear combination of these plane wave solutions. So, but just to note that this is a scalar equation. So what that means is that if I was given some position, some time, right, and I plug these numbers in here, and I know what the momentum and energy of the particle is, and then we're going to normalize the wave function to something, and usually it's 2 times the energy in order to preserve Lorentz invariant. This wave function just gives you one number, right? It's a complex number, but it's just still one number, okay? What we found with the Dirac Hamiltonian is, if we plug that into the Schrodinger equation, sorry, just pause. Okay, sorry, just had to blow my nose. If we plug the Dirac Hamiltonian into the Schrodinger equation, what we found is that these wave function must be these 4 component vectors because, right, the Dirac Hamiltonian turns out to be these 4x4 matrices. If you have 4x4 matrices, right, some sort of 4x4 matrices acting on some wave function, right, that wave function, just put a bunch of x's here just to illustrate. Have too many, right? In order for this multiplication to even make mathematical sense, right, you have to have, 4 things here, okay? And this creates, basically the mathematic forces us to think about the wave function as these 4 component Dirac spinners now, right, which is written down here. So instead of just a regular psi, we have psi 1, psi 2, psi 3, 4. And we're going to see that some of these are going to be representing particles, some of these are going to be representing antiparticles, and then there's actually going to be 2 spin states to each of them, so therefore we get 4. Okay, so once again, we expect the solution, right, to be some linear combinations of plane waves as usual, right? So there's this plane wave part, but what we're going to do is we're going to factor out this 4 component part. We're going to call this thing U, okay? And this U is going to depend on some energy and some momentum of this particular particle, okay? Where U is, this is known as the spinner factor, or actually it's just known as the spinner. Don't say the factor part, but it makes sense, right? You're just factoring out the 4 component parts, okay? Where this spinner, we're going to define it as just U1, U2, U3, U4, just as usual, hopefully. Okay, so this spinner, spinner is constant with time and space, but depends on the energy and momentum, right? So there's this explicit energy and momentum dependence in it. But what we're going to do is we're going to start off with the simplest case, okay? We're going to put this particle at rest and then see, we can just mathematically derive what the solution looks like, okay? So if a particle is at rest, the 4 vector of this particle, p mu, right, it's just going to be whatever its rest energy is. Its rest energy is going to be the mass, okay? And then the 3 component momentum is just zeros. Okay, so now we can actually write the wave function, with momentum being 0 and also momentum being 0 here. Remember, there's usually a p dot x here, right? Since the momentum is 0, that goes away also nicely. What we can do is plug this into the covariant form of the Dirac equation. Put it in here, right? Okay, and now we're going to have to start dealing with these gamma matrices and covariant derivatives, right? Okay, but with this simplest case is actually kind of nice, because since the momentum is 0, remember these covariant derivatives, right? Or these like 4 separate derivatives you're taking. If we are taking the, let me write the more general form here, right? So we can actually see why these things come out to be 0. To the minus I is the way of going backward. I p dot x minus et, right? So in general, right, these partial derivatives will bring stuff out, but since the momentum, this piece is 0, right, when we do this derivative with respect to x, y, and z, right, the derivative actually turns out to be 0 because, right, there is no x dependence in this wave function anymore, because, right, we make the momentum of that particle 0. So therefore, right, only the index 0 matters. Okay, so the indices 1, 2, 3 in the covariant derivative are all 0. For the index 0, which is the time part, we still have to deal with the time part, right? Because when this wave function still depends on time. Okay. When we plug that into the Dirac equation, we're going to see is that all on the left-hand side, right? We have gamma 0, and then in fact this is going to be mu 0, right? Partial 0, which is partial by partial t. And so what happens is that, well, let's just follow this little algebra track. Okay, the gamma 0 is out here, and then we're taking a time derivative of the wave function. The spinner part, right, does not depend on time, but the e to the minus I e t part does depend on time, so we have to do that derivative. When we do that derivative, we bring down a factor of minus I e. Okay, so just taking a partial derivative of that. Okay, we're going to factor out that I e, and then combine these two i's, right? I times minus I equals 1. Okay, then since the energy is just a scalar, we can move that in front of all the matrices. Okay, and what you end up with is that E times gamma 0, which is just some giant matrix, times U, which is this 4 component vector, and then we still have this factor e to the minus I e t at the end. Okay, and what I'm going to do is I'm going to highlight this piece here, show you that. Well, E is just going to be the mass, right? Okay, and gamma 0, did I forget the gamma 0 somewhere? Oh, yeah. This right-hand side actually comes from the right-hand side of this equation, so let me just rewrite that real quick. Gamma mu, partial mu. Okay, I'm going to rewrite it so that it's actually, right, like this instead, because that will make more sense for me. Okay, so the right-hand side of this equation, so this is all on the left-hand side, right? The right-hand side is just mass times the wave function, and the wave function is just u to the e minus I e t in the case that the momentum is 0. Okay, so this is the right-hand side. That's where this long equation came out to be. So this reduces the Dirac equation in the particle at rest case, right, to be just e times gamma naught, well, gamma 0 times u, because these e's can actually cancel out, multiplied by the mass times the u. Essentially, the u cannot cancel out, because, right, you have this gamma matrices multiplied by this 4 component vector thing. And so we're actually going to write this out with the gamma 0 here, right? And gamma 0 is basically the same matrix as beta. So this is 1, 1 with a negative identity matrix. It's just -1, -1 down here. So if you multiply this out, and then each of the u's, we're going to define the u's to be, right, these phi instead, just to make it different from the size. Okay, we plug write all these 4 component vectors and 4x4 matrices out, right? What we find is that, well, if you multiply this matrix out, this component multiplied by this component equals to this component, right? So the first piece here, let me just highlight them, right? This times this entire row, right, times this entire column gives you this piece here, right? Okay, since the other three components are 0, the only thing remaining is actually going to be phi naught. Here, let me just write this left-hand side of this equation out a little bit more clearly, right? So the first row, right, multiply by the column vector is going to give you the first row of the column on the right. Okay, so that's what's equal to the right hand side. Okay? That's what we're doing these matrix multiplications. Right? What that tells you is that whatever U1 has to be, right, it's going to be proportional to some normalization factor that's to be determined, right, times 1. Okay, so it's pretty simple in this case. It looks a little bit too simple, but yeah, we'll see that when we add in momentum, these things start mixing into each other. But this is just to illustrate the point that you're going to get 4 of these different spinners, okay, where for U2, right, whatever this, on this part is psi 2 or U2, okay, whatever you want to call it, okay, that's actually going to be similarly, right, instead of being in the first component, it's going to be in the second component. Okay, as I mentioned, this normalization factor is just going to be, you're going to save that for later just so we can preserve Lorentz invariance when we go to try to calculate cross sections and decay rates. Okay, so this corresponds to, right, all of this is going to be equal to the mass times whatever this wave function is. Okay, 0, 0, 1. Sorry, 1, 0, 0, 0. And where, right, this mass, right, is actually going to be equal to the energy of this particular particle. Okay, and these are the particle solution, meaning there are the solution that has positive energy, and the first component here, U1, is going to be the spin up particle, and then the U2 is going to be the spin down particle. Okay, for the index 3 and 4, okay, once again, if we define U3 to be equal to some normalization factor, and then put in 1 as the third component instead, right, what we're going to find is that this particular spinner is going to correspond to having the energy of the particle being opposite or negative of the mass of the particle instead. So these are the anti-particle solution, where this is the anti-particle, right, but spin up, and this is for U4, it's going to be the anti-particle but spin down. Okay, so there's 2 spin states and 2 possible particleness of things. So just to solidify this in a solid example, so for an electron, okay, right, you can have a spin up electron and a spin down electron. You can also have the anti-particle of the electron, which has the opposite charge, right, and that also have a spin up and spin down state. So you have 1, 2, 3, 4 different wave functions that describe the 4 different spinner that describe this one particular particle. So electron and an anti-electron, also known as a positron, is actually the same fundamental particle, but in a different spinner state. Okay, putting all these solutions together, okay, and then putting in the e to the I, e times t. Well, in this case, e is just the mass of the particle. Okay, the wave function for psi 1, right? So remember this is this 4 component psi stuff, right? 3 psi 4. So we're writing them each separately. Okay, if we, in this very simple case of the particle being at rest, right, the spinner just turns out to be 1, 1, 1, 1 in each of the relative position of the vector. But be a little careful in this case, right? The wave part e to the I mt part, right, gives you a positive energy in the for psi 1 and psi 2, but right, notice that the sign changes here for psi 3 and psi 4, and therefore it actually gives you the negative energy solution. Okay, all right. So that's the simplest case. So it looks really nice. So we can actually get this concept of particle and antiparticles. Okay, so this is the electron spin up, right? This is the electron spin down, right? This is a positron that has a spin up. This is a positron, or the antiparticle of an electron, spin down. Okay. Okay. What I'm going to do next is show you guys the general free particle solution, meaning now momentum is not zero. And there's a lot of math in this derivation. And since I don't think we should try to focus on that in this course, because we want to get through a lot of this material, but just get the qualitative and also knowing how we can actually write the solution as opposed to doing a lot of algebra steps to derive them. What we're going to do is I'm just going to show you what that solution looks like. And if you're interested, you can actually read through all the steps in Thompson. Okay, in the case that the particle is not at rest, right, the wave function now has some momentum in it, so some general momentum that we can't just ignore. Okay, the process is very similar above, right, where you plug in this wave function, but then now you have to deal with these alpha x, well, gamma 1, gamma 2, gamma 3 matrices. Okay, in fact, what Thompson actually does is that he revert back to these the alpha matrices. So it does involve quite a lot of algebra in order to write these, figure out what these spinor solutions are. But I'm going to skip over all that. But feel free to read those, okay, in the book. So U1, okay, which is the same one as, up here, right, which is the very simple one up here, where it's just normalization times 1 on the first component. You still have that in this case, right? But now, right, it has values in the third and the fourth component now. Okay, where those are going to be proportional to basically PZ in the third component, and then PX plus IPY in the fourth component, and it's all divided by E plus M. Okay. Okay. Right. So the way to think about this is that, well, these spinners now is not just a purely, right, one component per component, where this third component can also mix in with your first component. Okay. Okay. So U2, right, is very similar, right, except you basically kind of switch the X and the Y place. Okay. This is still the spinner for an electron with a spin up, right? And U2 is still the spinner for an electron but spin down. Okay. And then once again, U3, right, is going to be the anti-electron, also known as a positron, with a spin up. And then U4 is an anti-electron with spin down. Okay. 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 Notice that I think I gave this actually in your homework. If you take these momentum to be 0, it actually reduces back to the particle arrest solution. Okay. Okay. But what I want to tell you is that, well, the energy of these particles, right, for the two positive energy, meaning U1 and U2, okay, the energy of those is going to be positive, right, whatever the square root of p squared plus m squared is. Okay. I'm not 100% sure these absolute value signs are necessary, because I guess it could be a complex number, so therefore you want the magnitude of that complex number. Okay. Okay. The negative energy solution, namely U3 and U4, right, they're going to have energies of negative of square root of p squared plus m squared. Okay. So I'm going to wrap up this section, and we'll talk about antiparticles next.